In 1900, Max Planck, a German theoretical physicist, is considered the father of quantum theory, and he devises Planck's radiation law to solve the black-body radiation problem, which classical physics just could not explain. He introduced the idea that energy is quantized and uses the formula E equals h times nu, where h is Planck's constant, defining the quantum of action, and nu is the frequency of the energy. Planck's discovery paved the way for Einstein and the photoelectric effect. Planck won the Nobel Prize in 1918, and he revolutionized physics by showing energy is not continuous, but rather comes in discrete packets called quanta. "1905 was Albert Einstein's miraculous year. On March 17th, Einstein takes the idea of quanta and runs with it, describing the photoelectric effect and introducing light quanta called photons, laying the groundwork for quantum theory and winning a Nobel Prize in 1921 for this work. On May 11th, Einstein writes a paper on Brownian motion and provides theoretical evidence for the existence of atoms and molecules through statistical analysis. On June 30th, Einstein turns physics on its head with special relativity, redefining the concepts of space and time. On September 27th, Einstein deduces the mass-energy equivalence E equals mc squared, and for his doctoral dissertation on December 19th, he writes a paper on molecular size and calculating Avogadro's number using new methods. Truly a remarkable year for Einstein. In 1913, the Danish physicist Niels Bohr made foundational contributions to atomic structure and quantum theory. His 1922 Nobel Prize was earned by his proposition of the Bohr model of the atom. This suggested electrons orbit the nucleus in discrete energy levels. He introduced the idea of quantized angular momentum, leading to energy levels given by E sub n equals -1 over n squared. Electrons here jump between energy levels or orbits, emitting energy as photons. And he explained the atomic emission lines produced by hydrogen. He defines the Bohr magneton, or the electron magnetic moment. And he proposes that waves and particles are behaviors that are complementary and cannot be observed simultaneously. He was instrumental in the Copenhagen interpretation of quantum mechanics and shaped the philosophical understanding of measurement in physics. In 1924, Louis de Broglie, a French physicist, gave a revolutionary idea about particles exhibiting wave-like behavior. The matter-wave hypothesis he proposed was that particles such as electrons have associated wavelengths, just like light, and particle-like properties just like photons. His famous equation lambda equals h over p, where lambda is the de Broglie wavelength and p is the momentum of the particle. He unified the behavior of light and matter via wave-particle duality. In 1925, Werner Heisenberg, a German theoretical physicist, formulated matrix mechanics and the famous uncertainty principle, receiving the Nobel Prize in 1932. In his interpretation, observables were represented by matrices and classical variables replaced by non-commuting operators, operating on quantum states. His uncertainty principle states delta x times delta p is greater than or equal to h bar over 2, which imposes limits on simultaneous measurability. And the non-commutivity of quantum mechanical operators via the commutation relation, which equals I h bar, is at the heart of quantum theory. In 1926, Erwin Schrödinger, an Austrian theoretical physicist, formulated wave mechanics. And in 1933 he won the Nobel Prize for this formulation of quantum mechanics. The time-dependent Schrödinger equation, shown here, uses the Hamiltonian operator for total energy, and psi, the wave function, encodes the probability amplitude. The time-independent Schrödinger equation for stationary states in an atom has the Hamiltonian giving the energy levels of the quantum system. The wave function interpretation views particles like electrons as spread-out waves, not point-like particles, and the modulus squared as the probability density of finding a particle at position x. The thought experiment Schrödinger's cat illustrates the paradoxes of quantum superposition and measurement. And Schrödinger's legacy is in his equations, which are central to quantum chemistry, atomic physics, and even quantum computing today. The wave function truly is a miraculous idea in quantum theory. And Wolfgang Pauli, for Wolfgang Pauli's exclusion principle, formulated in 1925, says that no two identical fermions like electrons can occupy the same quantum state simultaneously. This fact explains the structure of the periodic table, governs the stability of atoms, and is essential for understanding degeneracy pressures in white dwarfs and neutron stars. He also introduced the Pauli spin matrices and predicted the neutrino. And there are many quantum mechanical founders that we could mention here, but for now, we will leave it at these superstars, and they are the ones who have truly developed the most accurate theory known to man, quantum field theory. After the success of Newtonian mechanics in an effort to simplify and generalize Newton's equations of motion to handle complex systems involving constraints or fields or many degrees of freedom, there's a shift in the emphasis from force-based mechanics to energy-based formulations of motion. Joseph Louis Lagrange, in 1788, influenced by the principles of least action and Euler's calculus of variations, he reformulates Newton's laws using a scalar quantity called the Lagrangian, which is the difference between the kinetic energy and the potential energy of a system. Now, this leads to the famous Euler-Lagrange equations shown here, and these use generalized coordinates given by q sub I. And these are ideal for systems exhibiting symmetry. This makes conserved quantities such as energy or momentum easier to identify. Then in the 1830s, William Rowan Hamilton, inspired by optics, develops a similar formalism to Lagrange, but used light rays and applied it to optics. He reformulates Lagrangian mechanics using the idea of phase space, with position and momenta referred to as the canonical coordinates, which have connections to each other. The Hamiltonian is given here by this equation, which incorporates the Lagrangian, but it calculates the total energy, and Hamilton defines the momentum in terms of the derivative of the Lagrangian. It's calculus done in phase space, and it converts second-order differential equations into first-order ones, with these equations giving the relations, and this provides a natural setting for the canonical transformations and what are called the Poisson brackets. The Poisson brackets become an essential tool in analyzing the structure and symmetry in systems. The Hamiltonian is a functional, meaning that it is a function of a function. Yet before Hamilton, in 1809, Simeon Denis Poisson was already studying the time evolution of observables in celestial mechanics. The Poisson brackets for functions f and g given here in terms of the difference of these partial derivatives, and it measures the interaction of two quantities under a system's dynamics. Now, why is this useful? In Hamiltonian mechanics, the time derivative of functional, f, is given here incorporating the Poisson brackets and the partial derivative in respect to time. This mirrors the Lie derivative in modern geometry, and it governs how something changes along the flow of the system. An important step in developing quantum mechanical theory. And in particular, these canonical structured coordinates obey these conditions. Now, what is the physical significance of this? Well, for symmetry purposes, if a function with the Hamiltonian's Poisson bracket is 0, then f is conserved. Noether's theorem in disguise. And generators, Poisson brackets identify quantities that generate transformations, such as angular momentum, whose components generate rotations. In the quantization process, the Poisson brackets become the commutation relations in quantum mechanics. Now, the canonical coordinates in quantum mechanics are given by the commutation relations, and the coordinates are actually operators with the little hat notation. The commutation relation is given here, which quantizes the units. The Schrödinger picture of quantum mechanics. The time-dependent Schrödinger equation governs the evolution of the state vector. IH bar times the time derivative of the function psi in the state vector is equal to the Hamiltonian operator times the state vector psi, psi being the wave function. The solution to the time-independent Schrödinger equation is given by psi is equal to e raised to the negative I ht over h bar times the ground state vector. And here, operators are fixed, time independent. Things such like position and momentum. Now, in the Heisenberg picture, state vectors are constant in time. Therefore, we may write the state equal to the ground state. And the time evolution is given by the operator, here given by e raised to the I Hamiltonian t over h bar, multiplied with the observable, and then multiplied by e to the negative I h t over h bar. Heisenberg's equations of motion are taking the time derivative of an operator because the time evolution is all within the operator in the Heisenberg picture. In quantum mechanics, a state vector is a mathematical object that completely describes the state of a quantum system. It tells you everything you need to know, or rather, everything that is knowable about the system's properties and how they evolve. State vector notation is given with a ket vector, given here, or the complex conjugate of that, a bra vector. So these are vectors that live in a complex Hilbert space, a complex vector space with an inner product defined on it. The state vector encodes the probabilities of all possible outcomes for any measurement. And if you know the state vector psi, you can calculate the probability of finding the system in some other state phi. You can calculate the expectation value of an observable, usually given with little hat notation, which is some measurable quantity. Now, for some physical observable, A, the inner product is defined here with the bra and ket notations. The superposition of two states, consider say states 0 and 1, a particular system might be in a superposition of these two where alpha and beta modulus squared are the probabilities of measuring the system in particular states, and the sum of those probabilities has to equal 1. Now, an electron is something called a fermion, which is called a spin 1/2 particle, spin being an intrinsic angular momentum quantity. Let's consider a particle in the following state, where the arrows indicate spin up and spin down, which are the two possible states for a spin 1/2 particle. And its evolution is governed by the Schrödinger equation, which gives a total energy through the Hamiltonian operator, and energy is an observable quantity. In special relativity, the energy-momentum relation is given by E squared equals P squared C squared plus M squared C to the fourth. Now when we switch to quantum mechanical operators, E becomes IH bar times the partial derivative d by dt. And the momentum operator is negative IH bar times del, the differential operator. Applying this to some state psi, we get this. And simplifying this, we get the relation here. Now, with some rearranging, we can get this into the following form. 1 over c squared d squared by dt squared minus del squared plus m squared c squared over h bar squared applied to the state psi equals 0. And using the D'Alembertian operator, which is the wave operator, we can reformulate this equation in this form, which is the 4-vector form. And this is known as the Klein-Gordon equation in flat Minkowski spacetime. In covariant notation, we choose the natural units h bar and c to be equal to 1. Then the equation reduces to this, applied to the state phi. And the D'Alembertian operator becomes this spacetime operator. And this is the Lorentz invariant version, which is suited for relativistic quantum field theory. Switching over to a curved spacetime, we get the Klein-Gordon-Fock equations, which we replace the partial derivatives with covariant derivatives, and the flat spacetime metric with a generalized metric, g mu nu. This gives us a covariant D'Alembertian here. And from this we can get the minimally coupled spacetime version to be this equation. And the non-minimally coupled version, including the Ricci tensor, or rather the Ricci scalar. And that incorporates the total curvature for the spacetime. The Klein-Gordon equation has a Lagrangian density given here, and varying the action with respect to phi yields the Klein-Gordon equations via the Euler-Lagrange equations. Relativistic quantum mechanics. What is a quantum field? A quantum field phi for a scalar field is an operator-valued function at each point in spacetime, and it acts as an operator on a Hilbert space. Particles are quanta of the fields. An electron is a quantum of the electron field, a photon is a quantum of the electromagnetic field, and so on. Particles are quantized by excitations of the quantum field, and each unique particle has its own quantum field. So you can think of a field as a collection of harmonic oscillators, and each mode, each momentum k of a quantum field behaves as a harmonic oscillator. The field is typically written as phi equals an integral over the space k divided by 2 pi cubed And then this expression here that incorporates something called an annihilation operator and a creation operator. And if we have a vacuum state applied to this operator, we get 0 for the annihilation operator. An example of a scalar quantum field for a real scalar field phi, the Lagrangian, is given by this expression. Quantizing this will lead to operators, phi and pi, satisfying the commutation relations that quantize the interactions. The delta with the little 3 on it is a three-dimensional Dirac delta function. It's a distribution spike. It's not a function in the normal sense, it's more of a statistical function, a distribution. Now, quantum fields also mediate forces. The proton field is the quantum electrodynamic mediator, where the gluon field is the quantum chromodynamic mediator, or for the strong force. And mass is a property of the field. Each quantum field describes a particle of a specific mass. So if we consider a field of a particle of mass m, m is a fixed parameter of that field. And fields acquire their mass via something called the Higgs mechanism, with interacting with the Higgs field. In the standard model of particle physics, often denoted by SU3 cross SU2 cross U1, many fields don't have mass terms by default because that would break something called gauge invariance. Interaction with the Higgs field is how particles acquire their mass. So the Higgs field is a field and has vacuum expectation values, or VEV, given here, meaning that this field fills the space and interacts with other fields via something called the Yukawa coupling, or gauge coupling. It generates mass in a dynamic way. Time to go down the quantum rabbit hole. Quantum field calculations. Quantum field theory in a flat Minkowski spacetime provides the framework for the modern theory of elementary particles. As incarnated by the standard model of particle physics, again SU3 cross SU2 cross U1, quantum field theory is an extremely well-tested model of physical reality. And there are two ways which are equivalent in approaching quantum field theory. The first is the canonical quantization method, and the second is using the Feynman functional path integral. Both ways have their pros and cons, their advantages and disadvantages. So let's explore the canonical quantization first. And this is taken to be a collection of position-dependent operators, one for each point in space. We adopt the Schrödinger picture, where operators are time independent, and the time evolution of the quantum system is encoded in the state vector, which has the wave function. Recall that in the Heisenberg picture, operators are time dependent. and quantum states are time independent. Sort of a flip-flop from the Schrödinger picture. Associated to each quantum field phi is a conjugate momentum density pi. These are operators, so they have little hats over them, and the commutation relation between the field and its momenta are given by this commutation relation, again seeing the Dirac delta function here. The Dirac delta function picks out a specific value. And this all generalizes to the canonical commutation relations given here, where this delta denotes the Kronecker delta. Many different deltas used in quantum mechanics. Now, on a technical note, this formalism lacks manifest Lorentz invariance. It can suitably be manipulated to produce the Lorentz invariant relativistic field theory. So, if one defines the local average values for the field and its momenta, here we have the average value of the field, and here's the average value for the momenta. Then we get the commutation relation to be negative I h bar over the volume of the region given by omega. Now, in quantum mechanics, one is used to solving the canonical commutation relations by going to the Schrödinger representation. And so the operators are given here. A quantum mechanical state is then just some function psi of the coordinate qi, and therefore the state is governed by the wave function. So the same thing can be done in the quantum field theory version, and here you'll see the momentum expressed in terms of a variation of a functional, in other words, a functional derivative. So it's like a partial derivative, but it uses deltas instead of curly d's. Now, one must deal with a functional derivative with respect to the field phi, and that's a little bit of a change from quantum mechanics to quantum field theory. So similarly, a quantum field theoretic state, psi, as a functional of the field phi, is now a function of time, but a functional of the field configuration. So let's consider a simple case, a free, massless, scalar field. The classical Lagrangian would be given by this expression, using the D'Alembertian operator. And the conjugate momentum, given to be this functional derivative, allows us to now look at the classical Hamiltonian. So the classical Hamiltonian, h, is given by this integral. And quantizing it, the functional Schrödinger equation is given here. So explicitly, one may write the Hamiltonian operator in this expression, using the functional derivative. And now, by analogy with ordinary quantum mechanics, the simple harmonic oscillator, one can now by inspection write down the ground state wave functional. So for the quantum field theory here, we get the following. The ground state wave functional is approximately equal to this exponential expression. And we note that the square root of the negative del squared operator is a pseudo-differential operator and is best understood under the Fourier transform. And that's where the k value comes from in these expressions. Often using the Fourier transform version is a lot easier to work with. Now the ground state energy is formally given here. The ground state wave functional is not normalizable in the usual sense, but more on this later. One of the key points here, though, is the ground state wave functional is peaked when the gradient of the field is equal to 0. And this formalism is used when one wants to estimate the typical size of a quantum fluctuation in the field. That is, when probed at a distance scale, say L. To this end, one defines the correlation function to be given here as measured against the ground state. And you see the Bra and Ket complex vector notation, which are Hilbert vectors. And in terms of this correlation function, one defines the change in the quantum field at measure L to be the square root of this correlation function, evaluated throughout a distance L. And to evaluate this object more efficiently, use a Fourier transform to momentum space, which then yields this expression. Momentum space makes the wave function more manageable, and the momentum space 2-point correlator is given here. Again featuring the three-dimensional Dirac delta function. So then the 2-point space correlator is obtained by taking the inverse Fourier transform. Pulling back the calculation yields this, and consequently we can measure the quantum fluctuations at a measure L using this particular formula, which is the square root of the correlation function. So quantum fluctuations become large at small scales. That is, as we let L go to infinity, the correlation function shrinks. Suppose one considers a field configuration such that the field is close to 0. That is, its fluctuations are small. Then the field differs from 0 by a small amount delta phi, and only in this region omega, and it's characterized by a distance scale L. Then we can estimate the ground state wave functional to be given by this expression. And we can do some simplification and rearranging. And thus, loosely speaking, the size of the quantum fluctuation is approximately the square root of h bar over L. Quantum fluctuations depend on the length L being probed. Thus, at smaller scales of L, we get larger quantum fluctuations. And in canonical quantum field theory, using the Schrödinger's picture is useful because it makes manifest the deep connections between quantum field theory and ordinary quantum mechanics. Particle physics calculations, however, are often more usefully carried out in the realm of Heisenberg, or even outside the canonical formalism altogether. In walks Richard Feynman. The Feynman functional path integral is an alternative to formulation of quantum mechanics equivalent to the usual canonical quantization techniques. However, in the path integral formalism, one expresses quantum mechanical expectation values a little differently in terms of the functional integral over all possible particle paths. And this is best carried out in actually the Heisenberg picture, where quantum mechanical states are time independent and the time evolution is encoded in operators. So one defines the expectation value of some measurable quantity chi as some quantum mechanical quantity chi of q being given by the integral and a capital curly D of q of t times chi of q times the exponential of raised to the Lagrangian integral, which is the action. This thing is called an integration measure of the set of all possible paths in the configuration space. So the capital D applied to q of t formally is actually the product, which is given by this large pi symbol, of dq of t, for t being a real number. This formalism is easily extended to quantum fields, and thus we get the following for the expectation value, again where S is the action. And this operator is a product of all the differential field components. The action, S of phi, is the integral of the Lagrangian. And for the special case that we have a free massless scalar field, the Lagrangian is given here by 1/2 the Minkowski metric d mu phi d nu phi. Let's make some technical notes. The transition amplitude between field configurations, or generating functionals, is given by z equals the integral of d phi times our exponential. Again, phi is the field, S is the action functional, and D is the functional integration measure over all field configurations. So what exactly is this object? Well, again, it's the product over all space-time points of the differentials of the field. This is a formal product of infinitely many integrals, one at each point in space-time. Again, the integral part coming from when this is in the integrand. Now, if we discretize space-time, allow us to make it finite in terms of point values, then we can approximate this product to n number of pieces, if you'd like, and then let n go to infinity, giving us the functional measure. So consider an endpoint correlation, we have the following functional, where 1 over z is the normalization factor. So the quantum mechanical analogy for a particle, path integral is given here, with the Bra and Ket notation for start and final outcomes. And that defines this integral here. So the expectation values can be calculated. And this is a measure over all paths x of t, connecting the initial starting point to the final starting position. Again, it's a sum over histories. Think about the action principle having fixed endpoints and looking at all the paths going from one point to another. In quantum field theory, this becomes integration over all field configurations, not just all particle paths. So in the Euclidean signature, Z sub E, one uses what's called the Wick rotation. And this is just a sort of mathematical trick for making the integral convergent and allowing the tools from statistical mechanics to be used. Now, in this picture, one probes the quantum fluctuations by defining the expectation value of this quantum fluctuation. In this form, the size of the quantum fluctuation seems to be related to the equal time behavior of what's called the Feynman propagator. And this has all to do with something called a Feynman diagram, which are used for particle physics calculations. Using integration by parts, and we get this value, where epsilon is a small difference. We can play out the wave function in the integral action. And we can absorb the I into that action, creating a Gaussian integral which is easily computed. Therefore, this function here can be found using this formalism. Again, the epsilon is introduced for convergence purposes. And we go to equal times. Again, we're working in the momentum space here. And we can use this integral to calculate expectation values. So finally, one can evaluate the quantum fluctuation as a square root of 2h bar over 2 pi L, and let's say for a massive free field, we can calculate the quantum fluctuation given here, where k sub 0 indicates something called a cylindrical Bessel function, a function in cylindrical coordinates. So now, suppose one knows the average field is phi sub 0 and is considering a field configuration of phi where phi differs from phi sub 0 by an amount delta phi, and over a spacetime region of size L. Then one can establish the difference in these particular actions in the following way. And if we approximate the action of the field to be 2 pi h bar, the field configuration interferes destructively with the average configuration. And then this suggests that the characteristic scale for quantum fluctuations at a distance scale L is given approximately to be the square root of h bar over L. So both theories approximate to the same value for quantum fluctuations. Correlation function, meaning the vacuum expectation time-ordered product of the fields. The 2-point function is a particle propagation amplitude, and I'll do a video at a later date on particle physics to give that more of a feel. If one thinks of space-time like a trampoline, classical matter is like placing balls on the trampoline and it warps the surface. But only so much. Quantum fluctuations are like vibrations and pressure pulses that create weird indentations, possibly allowing for tunnels, that is, for wormholes, to exist. Well, I hope you liked this video. Please stay tuned for episode 3. And please hit that like, subscribe, and notification button for more videos. And stay tuned for the next one. Thanks for watching.